Good evening, everyone. Could I ask you to take your seats and we'll begin this evening's event. I'd like to welcome you to tonight's Research Tuesday forum on sovereign defence. I'd first like to acknowledge the Kaurna people, the original custodians of the Adelaide Plains and the land on which the University of Adelaide's campuses here at North Terrace, The Waite and Roseworthy are built. My name is Julie Owens and I'm the Acting Deputy Vice-Chancellor Research and Vice President Research. So tonight we're turning our attention to defence. You may not be aware that our university in fact has a long and very proud history of collaboration with Australia's defence sector. So for many years we've worked extensively with both the Department of Defence and defence industry in an advisory capacity and as a strong research partner. We've established strong relationships with prominent government organisations such as the Defence Science and Technology Group, and of course we provide the sector with a constant supply of high quality, highly skilled graduates. What you may not also be aware of is that we're in fact the leading defence university in Australia. So for many years we have every year consistently received the most DSTG funding, well ahead of our nearest competitor interstate. So tonight we're going to hear about that university expertise in defence and some of the examples of specific defence projects that our researchers have been working on. We're first going to hear from Professor Michael Webb, who is our University Director of the Defence and Security theme, Professor Katrina Faulkner, Head of the School of Computer Science, Associate Professor Bruce Northcott, Director of the University's Centre for Defence Communications, Information Networking and its Teletraffic Research Centre. And Piers Lincoln, Institute Manager at the University's Institute for Photonics and Advanced Sensing, IPAS, which is our institute that's most heavily engaged in the defence arena. Now first they'll present individually, sharing with us some background about their current work. Following the presentations, we'll have all four speakers participate in a panel discussion where they can delve a little bit deeper into each topic. We'll then invite you, the audience, to offer questions. So to begin, let me first introduce and hand over the floor to Professor Michael Webb, who will lead the presentations and discussion. But first, just to give you a bit of background on Michael, he was appointed as the university's inaugural Director of Defence and Security in 2016, and in this role has been the key interface for industry and government seeking to partner with us in this area. He also holds the role of Deputy Director Defence at the Centre for Defence Communications and Information Networking. He has a PhD from physics from the University of St Andrews and a Master's in Mathematical Psychology, it's a bit worrying, from the University of Adelaide. Importantly, prior to joining the university, Michael worked in the Defence Science and Technology Organisation for more than 20 years, where he undertook and led research in over-the-horizon and microwave radar, signals intelligence, and command and control. So, Michael, can I hand over to you to the next stage? Thank you.
Thank you, Julie. Is that clear there? Thanks, Julie. And let me just add my welcome to you as well this evening. When defence talks about itself, it often uses the term capability and has some very specific ideas about what it means when it uses that term capability. It includes things like command and management, organisation, equipment, people, training and things like that. And it considers how these things all combine together to produce specific effects, specific capabilities. So for example, some key capabilities areas include intelligence, surveillance and reconnaissance. And so for this area, the capability depends on how the various types of equipment, satellites, surveillance aircraft, radar and people, organisation and training, how all that comes together to produce an overall effect. Other capability areas include cyber security, maritime and anti-submarine warfare, strike and air combat, and so on. I think you get the picture. What I'd like to do is talk briefly about the relationship between equipment and capability. And let me start with a couple of everyday illustrations. If you or I want to acquire a basic capability to communicate in text, one option would be to buy a pencil and paper with some basic education. We would have a capability to communicate with text. If we wanted a transportation capability, one option would be to buy a car, and with a bit of basic training, we would have a basic transportation capability. The point I want to make with these illustrations is that in general, you cannot take that kind of thinking and apply it to defence. Defence typically operates at the boundaries of its performance. It often takes both its equipment and people right to the edge, sometimes beyond. And that's just very different to just buying things off the shelf and with some basic training, having something. Thinking about these everyday examples, defence is much more like an artist who will no doubt know everything they need to know about pencils and paper. And it's more like a Formula One racing driver who will know a great deal about the car they're driving and will have a whole team who knows everything about the car. Merely buying equipment off the shelf will rarely provide defence with the kinds of capability it needs. Defence must have deep knowledge and understanding of all its capabilities if it is to operate at peak performance and with confidence. This is a key to having a sovereign defence capability. Probably should have that up. In 2016, Defence produced an industry policy statement with some profound transformational changes. For the first time ever in Australia, defence industry is now recognised as a fundamental input or a fundamental part of our national capability. Let me just say that again. Defence industry is now formally acknowledged to be a key part of our national defence capability. And of course, that's where universities' contributions to defence are also recognised. As Julie has mentioned, we educate the professionals that defence needs to operate effectively, whether that be in industry or civilians in defence or those serving in uniform. And of course, universities also undertake research, which is what we're talking about today, in many defence-related areas. They're always looking to push the boundaries of what's achievable and, dare I say it, what's conceivable. This same defence industry policy statement also outlines a new approach to defence innovation. It has a number of aspects, but for now it's enough to note that more than $1.6 billion in funding will be invested in defence research and innovation over a 10-year period. Much of this investment will occur in universities across Australia, and as you can imagine, that's got our attention. The University of Adelaide has a long and proud history of partnering with Defence, and in particular with the Defence Science and Technology Group, or DSTO, or WRE as some of you will know it. In fact, our very first full-time Vice-Chancellor, Sir Albert Percival Rowe, was also Australia's very first Chief Defence Scientist, although back then he was called Scientific Advisor to Defence. And of course, that was just the beginning for us. Since then, we've had extensive joint project with DST Group over many years. 4 funded chairs in various disciplines, large-scale funding for 8 or 9 concept technology demonstrator projects. We'll hear about one of those this evening. It's also significant that the Chancellor for our university is currently Rear Admiral the Honourable Kevin Scarce. You could say defence research is in our DNA. I had some trouble with this slide earlier. We currently undertake defence research in many areas. It's a very busy slide, I know. These areas include photonics and lasers, acoustic vibration and control, advanced electromagnetics, defence communications, military law and ethics, cybersecurity, mental health, and many more. Just last week, Minister Pyne announced $50 million of funding for a new cooperative research centre in trusted autonomous systems. Think drones with brains. That's a bit scary. An area in which we already have a strong collaboration with DST Group, so that's really quite exciting for us. As I'm sure you'll understand, we'll only be able to scratch the surface of what we do in defence at the University of Adelaide this evening. I wish I had time to talk about all of these exciting areas of research, where, for example, we have work on controlling the acoustic signature of our submarines, the development of wearable antennas for the military, work in high-energy lasers and novel radar techniques, some absolutely amazing work in machine learning, and one of my favourites, research into the neurobiology of the dragonfly, work that has been funded for over 10 years by the US Air Force. You know, the dragonfly is possibly the world's most successful predator. Once it decides on a prey, its hit rate is about 95%. This research has really sought to understand just how the tracking that the dragonfly is using it actually works. It works very well in very cluttered environments. What's really particularly interesting in collaboration with researchers in mechanical engineering and computer science, that work has actually now been applied in an autonomous vehicle, enabling it to navigate successfully in unstructured environments. It's really, truly fantastic work. But today, we'll only have time to look at 3 areas. I've selected areas that currently receive some of the most significant funding from Defence. We're going to hear from our Centre for Distributed and Intelligent Technologies in Computer Science. We'll hear from our Centre for Defence Communications and Information Networking, and from IPAS, our Institute for Photonics and Advanced Sensing. So, from Computer Science, I'd like to introduce you to Professor Kat Faulkner. Professor Faulkner is currently Head of School of the Computer Science in the Faculty of Engineering, Computer and Mathematical Sciences, and leads the Computer Science Education Research Group, as well as the Modelling and Analysis Program in the Centre for Distributed and Intelligent Technologies. Kat also has extensive experience in industry consultation, including work with DST Group, NICTA, now Data 61, Google US, Google Australia and New Zealand, the Commonwealth Department of Education and Training, and the Telstra Foundation, crossing both areas of computer science education and distributed systems modelling. Kat, over to you.
How does that sound?
It's got to be turned on.
Got to be turned on. Yes, that makes sense. All right, how are we going? Beautiful. Cool, thanks, Michael, for a lovely introduction. I'm going to talk today about some of the work that we've been doing within the Centre for Distributed and Intelligent Technologies over the last 6 years in a very deeply collaborative arrangement with our colleagues from DST Group. And this work is in the area of system execution modelling. And the aim of system execution modelling is to try and understand the performance of software systems within constrained environments, such as drones or combat management systems that you would find on submarines or equivalent military vehicles. The difficulty with what we're doing is that we're trying to understand the performance of software systems where the software systems themselves don't necessarily exist, and the hardware that we're trying to run the software systems on we may not have or may not exist either. And so we're trying to understand or predict basically the performance of software systems that will be operating within submarines and within other military environments in the future. And the constraints that we're talking about, particularly in defence systems, refer to the space, weight and power. And essentially what we're looking at is, in a submarine or on a drone, we have a very specific amount of space, an amount of weight that is allocated to support the computational hardware that we need to support our software systems. And there's only so much power that we're allowed to use for those as well. So any software system that we have within those environments has to guarantee that it's going to meet the space, weight and power constraints in operation. So often when we think of defence systems, we often think of, when we talk about submarines, we think of this. We think about the physical environment. And obviously there's a fantastic array of work, including work here at the University of Adelaide in that space. But our focus in the Centre for Distributed and Intelligent Technologies is very much about developing or supporting the development of software systems that process massive amounts of data collected by sensors across the systems. So the role of those software systems, combat management systems in particular, is to be able to gather, analyse, extract and process data coming in at a rate of thousands of data points per second, so that we're able to identify the key data elements that are needed by operators being able to make decisions in times of stress. The work that we do to support that, as I mentioned, is in the area of system execution modelling. And the idea that we work with is to build what we call executable models of the software system components. And these models model the flow of data through the system. Essentially, you can view of it as we have an equivalent software system. It doesn't actually perform the function that it's required, but it mimics the memory usage, it mimics the processing, it mimics the communications that occur between the system components. And these models we can then execute above the intended target hardware for our software system. So then we're able to predict, get an understanding of whether we're able to meet the real-time requirements of data processing, while at the same time meeting the space, weight and power constraints of the software system in question. Essentially what we're trying to answer is, given this particular software system and given this particular combination with hardware, are we able to make the decisions that we need to in the timeframes required? One of the interesting aspects when you're dealing with long-lived defence systems, such as submarines, is that you're having to replace and redevelop the software systems and the hardware during the lifetime of the system. So within our modelling tools, we're not just modelling the software systems and the hardware for the first time that they're incorporated into the system, but we're having to continue to do that. Every time we want to change the hardware, every time we want to change the software, include a new combat management system into our framework, we need to be sure that that particular combination of software and hardware is going to meet the performance constraints that we have within the system. And that can occur, on a rolling basis over the 20, 30 years lifespan of these systems. So over the last 6 years, we've spent a lot of time working on the design and development of a system execution modelling environment called Medea. And Medea enables us to build these models. We're able to model the memory usage, we're able to model the communications, the processing, using the expected algorithms of the software system that we're going to build. We're able to integrate live data sources so that we can incorporate the transmission of data that mimics that would be within defence environments. And we're able to incorporate both existing and models of systems. Because we may have situations where some of our software system already exists, some of our hardware may already exist. We're able to incorporate that along with the models of the system so that we can see how our new software component or our new hardware component might operate within that environment. And it's designed to target a variety of hardware options for performance execution. A lot of the recent work that we've been doing has been looking at FPGAs and GPUs, cloud environments, so that we can explore different hardware platforms for execution of our combat management systems. And the idea there is to try and optimise the space, weight and power constraints so that we're able to get the best system options for running the software systems that we need. One of the interesting aspects of the work we do, though, is that although a lot of our focus is very much on the design and support of combat management systems that would execute now or run now within our defence environments, we can also use these environments to explore future usage of combat management systems, or future usage of any kind of data environment, data analysis environment within constraints. And this is a really exciting aspect of the work that we do with defence, because we're able to explore new ways of visualisation, new ways of being able to interact and work with data, but also at the same time gain an understanding of whether they're going to meet the performance requirements of our submarine systems. The work that we do is very much focused in defence. As I say, it's a very strong collaboration for the last 6 years with DSTG. The software system that we've built, though, the Medea environment, is able to model any software system that operates within a constrained environment, not just defence systems. And so one of the high advantages of the work that we've been able to do is being able to take the work that we've been doing with defence and look to see what other usages we can use and we can apply it to within Australia. We've been working not only within the combat management system model for submarines, but we've been focusing a lot on the operational software of drones. And one of the projects that we've been looking at is how can we build models of drone software so that we're able to optimise the flight paths of drones based upon different environmental conditions. So depending on the height that a drone is flying at, depending on the amount of data processing that it might be doing, it's all going to impact the power usage and therefore impact the amount of time that it's able to fly. if we can model that information, if we can gain that, then we're able to optimise perhaps the progression of multiple drones across a particular fixed space. And one of the, I guess, really exciting projects that we've been working on recently is the idea of using this to be able to contribute to conservation work and agricultural sectors within Australia as well. I haven't been able to play with a baby wombat yet. It's my hope. But the recent project that we've been working on is around being able to track and monitor wombat populations that build their burrows underneath farming land. Currently, that's being done by people walking around with antennas and trying to get signals. So you can imagine that that's not overly efficient. If we're able to build drones that are able to fly over this land, track and monitor our little families of wombats, then we're able to better understand the impact upon the farming population, but also the impact of conservation attempts for different kinds of creatures. And so our recent work has been extending Medea to be able to build models of operational software for drones so that we're able to optimise for that particular category. So I think you can see that while defence work is incredibly important, it also has the potential to have benefit for so many different sectors within Australia. Okay, thank you, Michael.
Thanks very much, Kat. I need this back on, thanks. I'd like to now introduce you to Piers Lincoln. Piers is the Institute Manager for the Institute of Photonics and Advanced Sensing at the University of Adelaide. He leads the commercialisation activity at the Institute and works with scientific teams in that institute to help them develop their products, identify industry partners and new funding streams. Piers has helped drive medical, diagnostic, defence, mining and mineral processing, wine and environmental projects, and worked with the IPAS director, Professor Andre Luton, to build transdisciplinary teams across the University of Adelaide and across Australia to solve many real-world problems. He's a bit of a legend. Piers, over to you.
Thank you very much. Okay, so I'm Institute Manager for the Institute of Photonics and Advanced Sensing at the University of Adelaide. And photonics is all about light and how we apply it. And what we're all about at the Institute, we're based, headquartered in this building, is really about extending the limits of measurement, making new sensors that enable the world to make better decisions. We've got a core focus on working with industry. And last year we worked with 68 companies, and about 40% of the research dollars that came into the Institute were industry projects. So we've got a very strong focus on project management, project delivery. And we believe that this is an interesting new paradigm, because if you start with an industry problem, whether that's in defense or in mining, the constraints are massive. Karina mentioned earlier, space, weight, cost. So you can't just start with blue sky research and produce a device that costs $50 million, because you'll never be able to get it out into the world. So we find that working with industry really forces us to do much smarter science with what we've got and produce better devices. And that's been recognized. We work with a vast number of local companies who've tapped into the capabilities that we've got here. And what we find is that once companies have come into the university and worked with one group, then they'll suddenly find 5 other groups that can help them. So we'll often start working with a company developing a particular sensor, and then they'll realize they need software and artificial intelligence, and so we can plug in all sorts of the other wonderful bits of the university to help solve that problem and build a really good long-term relationship. And that capability has been recognized recently. We secured $1 million project from Mitsubishi in Japan on one of the sensors I'll talk about. And that's really pleasing that we're getting that engagement from massive global companies. We were born out of defense and their need to have photonics and sensors. But what we've often discovered, and I think we'll touch on this a bit later, is that once you've developed a sensor for one particular application, suddenly 5 other people from different sectors will put their hands up and say, we could do with one of those as well. And so we now span everything from defense, mining, mineral processing, astronomy, environmental monitoring, and food and wine, because our sensors are all about How can you get better decisions, better data, and make smarter decisions? So, as I said, we often start with a sort of a market focus, a customer who's often a company or a defence customer that has a particular need. We'll put this into our transdisciplinary melting pot where we bring together experts from physics, material science, biology, chemistry, engineering, maths, and harness all those skills, get everyone talking a common language, and what pops out the other end is really outstanding. Research creates new products, new jobs in the local economy. So we're best known for what's a kind of at the heart of a lot of our sensors, which is glass and optical fiber. And in this building, we have the capability of pretty much making any glass in the world. So if you want to make a sensor that works in the mid-infrared, you can't just use standard window glass. You've got to dope that glass with all sorts of rare earth ions that enable it to carry light of different wavelengths. And so we have the capability of, as I said, pretty much making any glass in the world in these special glove boxes, which protects the glass from the atmosphere as we're making it. We then process that glass and put structure into it. These aren't the type of fibers that you use for communications. They're specific fibers for sensing. And then once we've done that, we can draw that down into speciality optical fibers. And we have systems in Adelaide that can produce tens of kilometres of fibres in one run. And most of the sensors that we use only use 5 or 10 centimetres of a fibre. So we're already at an industrial scale, and that's really attractive to partners that we work with. And this is just a range of some of the hundreds of fibres that we've produced for doing everything from being, as I said, sensors, to being lasers, to carrying lasers around aircraft, to transmitting communications. So I'm just going to talk quickly through a few of the projects that we've worked on in defence over the last 10 years that we've been running. This particular example is an idea that was brought to us by our colleagues at Defence Science Technology Group. They wanted to be able to monitor very easily where corrosion was occurring in an aircraft. At the moment, aircraft have to be stripped down, the joints have to be stripped down and examined, and so they said, well, can't you just run a clever optical fibre throughout the structure? And so we developed an optical fibre that's run through a structure of an aircraft. Aluminium ions hit that fibre, you pass a light signal down that fibre, and depending where the corrosion's happening, you can measure in terms of time where that's going. You know, it takes 43 nanoseconds for that light to travel down the fibre. That means it's 23 meters along the fibre. That means it's lap joint number 12 that you're getting corrosion. So you instantly have a much quicker, cheaper, simpler way of measuring what's going on, and that brings down the cost and means you can keep your platforms running for longer. A fairly recent bit of work we did, led by one of our brightest and best early career researchers, Stephen Warren Smith, was the development of an optical fibre temperature sensor. This was originally done to enhance a biological sensor, but Stephen realised fairly quickly he'd developed a very high temperature optical fibre sensor. And we'd wanted to know for years what the temperature inside our furnaces was, but we didn't have the space to put conventional thermocouples in there. So we started putting these optical fibre sensors, and as we were doing a tour for a local engineering company, S.J. Cheeseman's, the managing director's eyes lit up, and he said, the smelter up at Port Pirie's wanted to measure the temperature in their zinc smelter for the last 50 years. And would this fibre survive at 1200 degrees in a highly corrosive environment? We said, of course it will. It's a piece of silica glass. So we took that, we put it into the smelter, and the smelter realised they've been overcooking the zinc for the last 50 years. So they're now saving several $1 million a year through being able to modify the process. And the joy of that was we've been able to take the results from that study, and a whole range of other partners have now started to adopt this technology, and we're producing sensors specifically for their applications. As hopefully many of you know, we have an incredible over-the-horizon radar system in Australia that projects the northern approaches. And that's centred around 3 main radar systems at Laverton, Alice, and Longreach. And at the heart of these radar systems is timing. The heart of each of these is a clock. And the director of IPAS, Andre Lutin, and his team have been working on developing some of the most accurate clocks in the world. These are based on sapphire crystals, and they lose 1 second every 38 million years. And so if you can harness a clock that accurately, connect it with a radar system, you can send out incredibly accurate pulses that you've got good timing signals on, then you can detect things which are more stealthy, moving more slowly, at a longer distance. And so when Andre and his team came here, the research group, the radar research group at the Defence Science Technology Group, were very excited. Didn't quite believe the data that had been put out in the paper over the years, but came with a truckload of equipment, plugged all their equipment into this box, went away smiling, and we've recently been awarded over $4 million in funding to help turn what you can see here from a lab-based demonstrator into something that can be plugged into the over-the-horizon radar system. And this is 4 of the now 8 team members out in the desert at Laverton at one of these sites. And this system is in the process of a multi-billion-dollar restructure and overhaul. And we're very hopeful that our clocks built in Adelaide are going to be all across Australia, helping to improve our defences. The final thing I just wanted to talk about is something else that we've got within IPAS. And this is really a capability that underpins the development and the creation of lots of our sensors, which is how do you build sensors more quickly? How do you build highly customized sensors? And so we created and added onto our advanced manufacturing team a capability in metal printing. And so this allows us to put down layers of powder and using a laser fuse those into solid structures. And this is a beautiful technique for devices that are either very small, very complex, low numbers of runs. And it's the kind of thing that fits beautifully within a university environment because it's not just a question of buying a printer. You've got to have all the design capabilities, the engineering capabilities, the characterization capabilities to actually understand what you've made. Now, here's just a couple of projects that we're working on in the defence space at the moment that highlights how that works. We work with a group of engineering students who designed what's the smallest jet engine in the world. And so this enables you to generate considerable power. And this group have formed a company after working at the university, EcoJet, and they're going on to bigger and better things, and they're having extensive conversations with defence who want micro-generation of power in remote sites. The other example on the right-hand side here is part of the submarines. Now, we only have a few submarines here, and many of the companies that used to produce all the original parts have long since ceased to exist. And so 3D printing is a really excellent way of producing the very small numbers of parts that those submarines need to keep running. So we do a lot of work with the Submarine Corporation on that. Just want to show you one very quick one of another company, just in case anyone has any projects and ideas. So local company Maptech, who makes some of the world's best laser scanners, came to us with a design of an optical chassis. And this was conventionally made in 3 parts. And they said, can you make one of these in 1 part by 3D printing? And we said, of course we can, but that's not really optimized for 3D printing. And they said, well, that's what we want. And so we gave them the first part, and then we gave them what they should have asked for, which was 20% of the original weight, so 20% of the material, which meant we could print it a lot quicker, and it was just as strong. And at that point, the light bulb went off in the managing director's head, and he said, this is fantastic, because we can probably take 25 kilogram laser scanner and make that 7 kilos if we apply this to every part of that scanner. So, as I said, if you have projects, if you work in engineering, come and have a chat with us, and we'll see what we can do to help. So that's a bit of an overview of what we're doing now. And in terms of our 1,000-year vision, well, the sky's the limit. Thank you.
Thanks, Piers. Fantastic. So finally, I'd like to now introduce Associate Professor Bruce Northcote. Bruce is currently Director for the Centre of Defence Communications and Information Networking at the University of Adelaide. He's also CEO of Talari. Talari is a commercial venture launched within the university to help mobile network operators around the world more effectively manage their capacity.
In these roles, he brings his considerable communications engineering and consulting experience to bear on projects for defence as well as for commercial clients. Of particular note is that Bruce worked for nearly 6 years in the US during the internet boom of the mid to late 90s, surviving the tech crash of the early 90s as an independent consultant prior to coming here. One of the features of that centre is the people in that centre nearly all have substantial industry experience. Bruce, over to you.
Thanks, Michael. I have to apologise straight away. I don't have a cute wombat and I don't have a Death Star. I don't have really cool toys. Our area is communications network engineering. So we're all about understanding the performance and the capacity of the communication systems that exist today. I'm going to lead you through a little bit of history. I'm trying to establish some credentials and talk just briefly about some of the work that we're doing for defence. I hope you do realise that once we start talking about communication systems, a lot of it is very highly classified and we won't go into it. So first, let's establish some credentials. The centre I'm director of, I'm very proud to be director of, there's a great group of people in it. We were established over 30 years ago by then Telecom Australia as a centre of excellence in telecommunications engineering. We've had an ongoing, continuous relationship with them. We have consulted to Telstra on every single technology refresh they put into both their fixed and wireless networks in that time. When Frank Blunt came to Australia as CEO of Telstra from the US, Telstra had consulting contract relationships with 14 universities and he cancelled all of them except ours. Somehow we were able to convert what we were doing then as Blue Sky Research and make it very directly applicable to their business, and I hope we're still doing that today. The biggest project that we've worked on in the last 10 years is all about capacity management of the cellular networks, the mobile networks for Telstra. It's our biggest thing. It's the thing that we're taking worldwide and commercialising, and that was the Tulare experience that Michael talked about. And it's through that credential that we've been able to consult and have relationships with all of these international network operators, some of the biggest and largest in the world, AT&T, Vodafone. The Ooredoo Group itself owns something like 14 different network operators. So we're taking the work that we've done here with Telstra, we're commercialising it, and we're sending it out into the world as world's best. Using the software that we've got, this Tulare software, Telstra has managed to become one of the most CapEx efficient operators in the world. They don't spend money on their network unless they need to, but they're managing the network so that it can ensure a certain customer experience everywhere. So that's this Tulare venture that we're talking about, and our worldwide partner for sales and distribution is InfoVista. And we're hoping that that goes really well. The thing about working with defence is that you have to survive long enough to be successful. Back when Frank Blunt was cancelling research contracts, we started to get very worried about our longevity. Were we going to lose our sugar daddy in Telstra? We're very good at communications engineering and performance analysis, so what could we do? We didn't really want to go and work for Vodafone and Optus because that might have been kicking ourselves in the teeth. The Pump runs the third largest network in Australia, and Telstra did not mind us going to work for them, so it was really back in about 2003 that we started getting serious about perhaps translating some of that capability into working for defence. Of course, there are much bigger problems than just communications engineering. We have other capabilities. We have a very large data analytics capability as well. So we've worked with a lot of these companies, including our own Adelaide University. We do a lot of optimisation of various things like timetabling and facilities management for them. That's credential. You need credential to even have a conversation with defence. All right? The first couple of meetings we were having back in 2003, they really didn't want to talk to us. There's one project that I'm going to talk about at the very end that it took 5 years before we even got to the point where we could start working on the contract. We have to survive long enough to be successful in this area. This is just a screenshot of this Tulare software project. What I'm showing you here is really all the cell towers of Telstra around this local neighbourhood. Tulare, what it actually does is it provides a unique software model for every single cell sector carrier, every cell for every hour of every day of operation. It's a unique model, and it's very heavily customised to try and determine what kind of user experience is happening now and translate that to work out when will that user experience degrade below what is acceptable to Telstra so that they then know when they have to start planning a capacity expansion. Capacity expansions in cellular networks take about 6 to 9 months to plan, so you need to know 6 to 9 months in advance. So having a forecasting capability is really important. Mathematical analysis, engineering, all sorts of things go into that. This next slide is one of my favourites. What I'm showing here, you don't need to be able to read it, but the y-axis is showing the percentage of cells in the entire Telstra network that are not meeting the performance targets based out of our modelling. And Telstra likes to operate between 1% and 3%, 5% of the network with some capacity problems, because then they'll start spending money when those engineering objectives are exceeded. I'm just going to zoom into one area. November, December 2008. That was when the first 3G iPhone came out. And as soon as it came out, the Telstra network started performing very badly. And Telstra were very concerned about that. And it was through use of our software that they detected it. It turns out that implementation of a phone came with some flaws in some of the software. Some of the protocol implementation was done badly, and it caused a problem in terms of consuming more resource of the network than most other phones did. Telstra detected it. Telstra was the first network operator in the world to detect this problem using our software, got Apple to fix it, and sure enough, a few months later, the network started behaving properly again, which is why you see that dip back down. The message here is that even with great technology, it still has to be fit for purpose. Right? If it's not managed properly, if it's not deployed properly, if the right configuration settings aren't used, it can have a very bad effect on the network. And imagine if you're a warfighter out there and you've got a piece of equipment that's incredibly sophisticated, but it's not quite configured properly. It's your life we're talking about. Of course, that next bit, that's the second iPhone. But they did it properly this time. That wasn't a protocol issue. That was actually just consumer demand driving up the requirement for more capacity in the network. That's pretty cool stuff. All right, a bit of a history lesson coming up now, and now I have to go to my sheet of information because I've got some dates coming up. This is very early 1900s or perhaps late 1800s. It was in 1844 that Samuel Morse did the very first long-distance communication of a telegraph message. That was just Morse code. It's does. 1876, Alexander Graham Bell did the first telephone call from one room to his assistant in another room. By 1892, telephony was so pervasive, so popular, that we had this massive wire stack appearing in cities around the world. Just in those few years, it went from nothing to just boom. The thing with this kind of communication network is every single link there is a point-to-point link. If I wanted to make a phone call to Julie, I had to have a wire going to Julie. If I also wanted to make a phone call to my mum, I had to have a wire to mum. So I had lots of wires, right? Really, configuration is simple. You put up a wire, it works. So that's cool. But obviously there's complexity here that was unexpected. Let's talk about war. This is now 1917. We need to communicate between soldiers and officers and forward observers back to base and all that kind of stuff. We can't have wires running everywhere, so obviously radio started kicking in as a useful technology. The very first radio signal was discovered in 1880, the ability to actually transmit useful data over radio, 1880. The very first radio broadcast was done in 1906. This is just 11 years later. What we're seeing here is that in times of war, certainly in the communication space, there's massive advances in the use of communications technology, and it's still true today. Notice here what the soldiers on the right are doing. They're actually cycling to generate power for this. So as Katrina says, power is a very important issue for defence, right? We don't have cyclists running around with our soldiers anymore. You saw that complicated picture of all the wires up there. It was also in times of war that they developed the very first really good use of an actual exchange. All right, so now we're simplifying the management of networks in intelligent ways. After the war, it translated to commercial space. So this is the commercial operation of a switchboard. telephony very soon after this became so popular in places like New York that the switchboards, where they had to patch from one wire to another wire, became so large that the network operator put on roller skates to go from one end of the switchboard to the other end. Technology and the use of technology just went through the roof. So let's talk about where we are today. This is a picture taken not that long ago, 2010, of a soldier in Afghanistan. What's he got there? He's got a very little foldable satellite dish where you can just set it up, very lightweight, and point, and he's got instant communication. It's pretty incredible. Of course, the use of satellites for military and civilian use is going gangbusters. The bandwidth of the satellites that are up there now is absolutely incredible. The fact that using the NBN we can cover those parts of Australia that aren't wired or wireless cellular technology with bandwidths that are now as equal, above the 12 megabits per second. That was the first claimed bandwidth speed that the NBN was going to be built at. And of course, then we've got this. Katrina talked about the submarine and how the submarine is really a big data center and it has space, weight, and power issues. This thing and the use of this is going to absolutely blow data consumption out of the water. This is a data center in the air. The requirements of processing and the sensors that this machine is going to bring to Australia and to the other forces that have it are absolutely extreme. So similarly, there's space, weight, and power issues for a submarine. There's space, weight, and power and data processing issues here. A lot of the stuff needs to be processed on board so that the communication systems, the communication bearers that are attached to this only need to transmit the post-processed data, and that's really important. So from a communications perspective, the really important issues for communications networking, there must be a low probability of detection, low probability of intercept. We have to be able to have connectivity in times of jamming. Obviously, we've got very high mobility, very fast things, but mobility in all areas through all terrains. So terrain becomes really important. Line of sight communications can get impacted by bombs, by hills, by everything, right? And of course, weather impacts satellite communication very heavily, but a lot of these other communications technologies are impacted by weather. So a lot of the work we're doing in my group is to help demonstrate to defence the fitness for purpose of whatever communications infrastructure they're trying to deploy for those specific types of missions. Sure, it's great if your radios work here in Australia when you've tested it in the field just up the road at Edinburgh, but what happens if you take it to Dili in the middle of a monsoon with much higher hills and all that kind of stuff? And we've set up infrastructure in my centre to be able to emulate those environments to demonstrate to defence whether what they have is fit for purpose. You can't just assume the network. You can't just assume that the equipment you're taking is going to work. And as Mike said in the absolute introduction to this, the warfighters are working on the absolute extreme of capability. And if they don't know in advance that what they take with them is going to be fit for purpose, then there's going to be some very serious consequences. And of course, power. It keeps coming back to power. We can give the warfighters some incredible equipment, but if they don't have the batteries and the power to be able to operate it, then there's also going to be big issues. So where are we going civilian technology? We're now at a point where civilian communications technology is actually, again, accelerating faster than military development. In World War I and II, the military side of communications technology drove civilian and went the other way. This thing here, this Ericsson dot radio, it's about that big. You can mount it on a lamppost. That is a 4G cell. It's a 4G mobile cell. So that can actually be mounted on a drone. We can now give a 4G cell with high encryption on a drone to the military, and they can instantly set up a communication system like that. That's pretty powerful. That's pretty incredible. And what have we got coming? This is a photo I took just this year in Barcelona at Mobile World Congress. This is a proof of concept of 5G. You've heard about 5G coming. I don't know if you can read the numbers, but that is a proof of concept 5G cell, and it's operating at 5.2 gigabits per second over the air. Think of what that's going to do. It's going to just blow this away. All right. So I talked earlier a little bit about our network emulation environment. It's all about evaluating fitness for purpose. Trust me, over the last 30 years, we've developed models of just about every communication bearer and system you can think of, even the tactical ones for defence. So what we do is we use that modelling network emulation environment to advise the various major projects in defence about whether what they have planned for the communications aspects of their projects is fit for purpose. It involves a lot of human-in-the-loop and system-in-the-loop testing. We can actually emulate networks of arbitrary complexity, but we can also plug this emulated network into real network components. So we can have soldiers actually using the real radios that are then plugged into our model of a network that perhaps is a much larger battle space. I'll show you what I mean by the complexity of that. This is the type of complexity we're heading towards. We've got AWACS, that's that 737 plane with the big hump on it. That's one of the world's most sophisticated sensing systems. The Australian is absolutely leading the way in that. Obviously, we've got satellite data. We've got these brand new planes that are going to be massive data sensors in the sky, all sorts of communication systems. I'm going to focus on just one of them that we're working with at the moment. The little infantry people there on the ground. Now, I said we could fly a drone with an LTE network for them, 4G network, but what they're actually procuring at the moment is this advanced radio technology where you simply just turn the radios on and they self-configure and form their own mobile ad hoc network. So these radios aren't very high powered, they don't go very far. Perhaps if you're in a battalion of 300 soldiers, if I wanted to talk to the furthest soldier, I might have to go through 3 hops. My message will go to the next radio, to the next radio, to the next radio. These are self-configurable radios. Right? So it actually takes some effort, some resources for those radios to maintain a self-configured mesh network. But when you're deploying resources just to the management of the network, that means there's fewer resources to actually transmit traffic. These radios were being tested in the lab out at DST and proven to work beautifully, really high bandwidth. They only had, I think, 14 of them. The Army, when they went to test these radios with a larger scale, came back saying, these radios aren't working as well. They came to us to find out why. So we put them into the network emulation environment. We matched the test results out of the lab, and then we went to scale. I think, I'm not sure the numbers of how many radios they had in the field, but we went all the way up to 300 radios in a self-configurable network, and we were able to prove that if you didn't configure them, if there are a few settings that weren't done properly, the throughput end-to-end on this self-configurable network just collapsed. Too many resources were going to the management of the network and not to actually providing end-to-end throughput. So this self-configurable capability just wasn't fit for purpose unless it was managed properly. And I guess that's my final key point. You know, we can create the most sophisticated of communication systems, but unless they're managed properly, our warfighters won't be able to operate at the extremes of their capability. And that's really essential. Thank you.
Thank you, Bruce. What I'd like to do now is invite Kat, Bruce and Piers to sit here, and we'll just do a little bit of Q&A. And I've got just 2 or 3 questions here, but then we'll throw it open to the floor for questions if you have some. Okay. So with all the defence-related research going on at the university, you would have thought researchers must be pretty interested in defence, working in defence. I'm just interested to understand what your thinking is about what it is that makes working in defence, doing defence-related research, interesting. So.
I'll take it from the start. I kind of told the story already. My centre was at risk of losing funding from our biggest customer, and we really needed to find a backup plan. Knowing that defence has the 3rd largest network was just such a natural fit for us. Luckily, Telstra still kept us funding for a long time and still does. they're still our largest customer, because it took 5 to 6 years for us to get traction in defence. So it was a long courtship, as it were.
So you're saying it's the money?
For us, it was the money.
Thanks.
I guess for us, defence is a wonderful customer, particularly when you have something like the clocks, where suddenly something goes from being something that's nice to have to something that's need to have. And when you can find a match like that, the money flows incredibly quickly, incredibly easily. And so long as you can have people in your team who can talk defence language, and that's the joy of us having centres like the one led by Mike, then you can build a really good long-term trusting relationship, and that's what we enjoy.
Just thinking about that clock, I know it was about 12 to 14 years in the making, so it's a long-term investment from a research point of view before you get to where you are today.
I think from our perspective, it's very much about being able to deal with real-world problems. We love what we do, and we're very interested in obviously the theoretical foundations of the discipline that we work in. But there's nothing more exciting than being able to deal with people who are actually going to use what you're doing, with a real problem that's just going to help motivate all sorts of new questions and new ways of thinking about what you're doing. And being able, and in particular with defence, I think it's because it's very genuinely collaborative as well. And so we work very closely with our defence partners. We speak to them every week, and they're on campus with us. And so it's not just a matter of, oh, they gave us an idea and some money and off you go, you come back 6 years later. We're working together to try and solve these problems, so these real problems that are actually going to have real impact.
Yeah. I guess that's one of the things I've noticed. They talk a lot more, DST particularly talks a lot more about partnership now, and we really are building genuine partnerships, which is exciting. It seems to me that a lot of the applications we've talked about here actually have multiple disciplines. They're not just singular in focus. So I was wondering if you just perhaps just talk a little bit about the interdisciplinarity of the work you do.
Well, I'll start and then we'll head back again.
Yep.
I think one of the most exciting things about the work that we do is actually we work very closely with Bruce's area, because we have the research expertise to build the system. Bruce's area has the defence expertise to be able to apply it and demonstrate it to defence. And so we actually have a three-way partnership with defence, and that's been an absolutely fantastic way of being able to not only have a real-world problem, but then also be able to apply it to the depth that you need to for a research application.
Fantastic.
I guess our entire institute is built around transdisciplinary teams and bringing people together. And so, we will need to bring, an end user that has a problem, and then to solve that problem, you'll need to mathematically model that problem. You'll need to create the right materials to solve that problem. We're working increasingly with the mathematicians to create theoretical models so we can make a fibre the first time rather than having 5 goes at it. You've then got to have chemists who can add structures on the outside of that fibre to turn it from a piece of glass into a sensor. If it's a biological sensor, you've got to have biologists who can add antibodies. You've got to have clinicians who can then take that sensor and put it into a person to make a measurement. So we love creating these teams, and one of the things we've learnt is that scientists all speak different languages. They use different units of measurement, and we've sort of built a team now who actually can talk each other's languages and aren't afraid to say, excuse me, what does that mean? And we find we get a lot more out of that approach.
Dimensioning communication networks used to just be a mathematical problem. I got a PhD in mathematics, so I'm not really an engineer, although I pretend to be. When you're trying to work out how many circuits to deliver an appropriate telephone capacity to a city of a certain size, between cities and all those kind of things, that was just mathematics. The communication systems and technology is now so complex that we need physics, we need computer science, we certainly need electrical engineering. There's so much, if you think of the different layers of the technology stack, we've got the physical layer, and being able to understand radio waveforms. We need to understand weather and terrain and the impacts of weather on satellites, and then there's the actual capacity management of these systems. So we need to understand how the intelligence of, say, an LTE a 4G cell, how it actually allocates resources. So then we have to have modelling expertise, which is not mathematics anymore, but clever thinking and computer science. So it's all multidisciplinary now.
Yeah. And there's very much a human piece. You really do focus on user experience very much with a lot of your modelling, and that's where things can come unstuck if we don't understand that. We've heard this evening a fair bit about commercialisation. I was wondering, what is, in your experience, what have been the main challenges that you've had to face in commercialising what you have, turning good ideas into products and services?
I'll start again because we're not successful yet. I think this is another one of those examples of you need to survive long enough to succeed, just like getting into defence work. This commercialisation of this technology, yes, it's been fantastically successful with Telstra, and we have used it to consult to all these network operators, but we're not making bundles of money out of it. So having a diversification in what we do is absolutely necessary for us.
I'd say the critical thing is about getting sufficient funding. The clock system, was 15 years in the making before it got to what's called a technology readiness level 3 product in the lab. That's now got to be taken up to a level 7 out of 10. And that takes millions of dollars to take something that can be operated by a number of sort of PhD trained people to somebody, in the military.
Sure.
And so, that's the joy of being where we are, that we can call on a lot of resources and build big enough teams and work in partnership to actually find out what does the customer need. Because often within a university, you'll build what you'd like within a university, not what an end user requires. And that takes a lot of time.
Our focus is somewhat different in that from the outset of our collaboration with DST Group, their focus was, yes, on building a modelling capability, but was also on building the awareness that this is an appropriate technique to use within defence environments, the design of defence systems. And so right from the outset, we had an agreement that everything that we produce, so Medea, our full modelling environment, is all open source. And that, of course, then means that we can then release that so that other people can use it. We can build up the capability, the people capability of being able to use these kinds of modelling environments across the defence industries, but also other industries. And that, of course, presents its own challenges in that if you're going to release open source software, you have to make sure that it's robust and well documented and actually works. And so that's one of the things that we've had to really focus on, is making sure that that quality is there in the production.
Just a last question. Thanks for that. Last question. I think we've all of you have significant relationships with DST Group. I'm just wondering, could you comment on how that relationship you have with them has evolved over time?
Well, again, I guess, because ours is actually quite a detailed collaboration, I think initially we started with very much scoping exercises. So we spent a lot of time just trying to talk through ideas, talking through projects to see what would be of potential interest to both of us. I think that's the same whenever you're working with any industry partner. You don't come in as an academic and know exactly what their problems are, and they don't know what their solutions should be. So you have to spend a lot of time working together and scoping out project work. But now, after 6 years of working together, we're able to start to think about the more advanced problems. So rather than thinking about the immediate problems that they have that year that they need to deal with, we're able to think 5-10 years in the future to start to scope those out instead.
Okay, so you've got some trust running, clearly.
I think that's the key. I'll just sort of echo that. As you build that relationship, you build, and it goes from here's a small chunk of money, prove you have that capability, prove you can solve those problems, and it gets to the point where it truly is a partnership. And when problems come up on both sides, they're jointly shared problems, because you're both after solving the same goal.
Great. Ours wasn't really a planned activity, but I think about 15 years ago, one of our staff members left my area to go and work for DST. And in those 15 years, he's been promoted and promoted. So now we've got to a point where we know people very, very well at some quite senior levels within DST. And those very long-term relationships are now bearing fruit. But just like Piers said, firstly, you have to pick the low-hanging fruit, find a problem that you can fund to a low level to prove the capability, to then get the trust, and repeat and repeat, and have another meeting, and do it again. So it's a long-term relationship. Alex Zelinsky, 2 years ago at the DST Open Day at Edinburgh, first started talking about the fact that DST really wants to start partnering. And I was sitting in the audience and I wasn't really sure whether that was going to come true, but in the last 2 years it's massively turned around. It truly is partnerships we're seeing. We're finally seeing long-term research contracts, not 3 months here, 5 months there, but multi-year, 2-year, 3-year research contracts coming out, and that makes our life so much easier.
Terrific. I think I'd like to throw it over to you if there are any questions. We have a roving mic up there.
Hi, my question is to Kat and Bruce. When we went from 3G to 4G, I had one phone that was 3G and then another phone that was 4G. How would the software cope with 5G, and how long will it take for 5G to be around? Like we've got 4G now, so everyone can be 5G. How long will that take, and what sort of software in the phones have to cope with that 5G?
Very technical question there. Right now, the network equipment manufacturers and the major network operators are testing 5G prototypes in their labs right now. They have developed the modems to operate. The 5G hasn't really been defined as a standard yet, but they've already worked out what the use cases are going to be. Massive ability to support millions of handsets, not just in a per square kilometre area. So we're talking about the Internet of Things. We're talking about very cheap, low power devices, also operating in the same network as our premium smartphones, where we want everything done faster. We want to be able to download a video in seconds and those kind of things. So firstly, the standards haven't been finalised, but I think we know where we're going. So with a non-finalised standard, it's very difficult for the equipment vendors to go out and build it, but they are already testing prototypes. The cell towers and the antennas up on the cell towers, they're going to have to be upgraded. The handsets will definitely have to be upgraded. The phones are going to require, at the moment I think in the most advanced 4G phones at the moment, in our handsets we've got 4 separate antennas, so we can do 4x4, what they call MIMO, multiple input, multiple output. These new 5G capabilities are probably going to need 16 antennas inside a phone to be able to get to the bandwidths we're talking about. So phone design is going to radically change. The software to drive it is going to be faster and faster. At the moment, the communication between your handset and the network can adjust the resource allocation to your phone 500 times a second. So if you think about all the other people that are operating in the same location as you, 500 times a second, the network is deciding who gets the resources, who gets the bandwidth. That's going to change to be even faster. So there's massive complexity.
Hey, going, Matthew Lerner. If funding was to increase, where would that actually go? And are we actually doing some of the same things as other states? There you go.
Sorry, so if funding is to increase, where would it go, is it?
Yeah, would it go into greater depth or other things that you have maybe planned or training? Or?
So a lot of our funding does, as you've heard, comes from Defence and through DST Group very often. DST Group, in that Defence Industry Policy Statement, identified 9 key areas where they want to focus their investment, and so that's where the funding will go. Those key areas include intelligence, surveillance and reconnaissance, and technologies that support advanced sensors, they're in directed energy effects, it's in quantum technologies and medical countermeasures. So yeah, there's 9 areas. So I guess Defence knows where it's going. We're watching that very closely. We know where our strengths are, and we are gearing up to be able to respond to the opportunities as they emerge.
Evening, everyone.
So interstate, a couple of interesting things there. Piers, do you want to talk about what we're doing in quantum technologies?
I guess the thing is, these days you've got to collaborate in order to get funding. And so if we just go in as the University of Adelaide, the chance of winning a lot of these major projects is very slim. So what we'll find, and this is an area we're working in quantum sensing, is we're partnered up with the other leading universities in the country, the Australian National University and University of Queensland. And what you do there is you bring together highly complementary teams and create something that's got far greater capability than just one university going in together. So often it's not just what you can do alone, it's how can you be smart and work together.
Thanks.
Evening, everyone. Thanks very much for that. Look, there's loads of questions could be asked, but where does this all end? And Piers, your over-horizon radar, I've heard in the region of $1.2 billion is getting spent in the next 10 years. And we keep saying that Australia is leading the field. Surely, if Australia's leading the field, you can get more money from other governments. We're spending just a mere 1.2 billion on over the horizon, and then there's all the other stuff going on. Surely other governments like the Americans and the Chinese, the Japanese, have got loads of money to pour into this sort of projects as well. So do you really need to go out and market it yourself, or can you get the government to help you market it? Because at the end of the day, it's them who wants a dollar.
Do you want to start?
Interesting question. So there's a couple of things to say. There are a couple of prime contractors that currently run the over-the-horizon radar network. That's Lockheed Martin and BAE. And I understand that at least one of those companies already exports its technology. It's obviously under some kind of degree of control, so we don't export the really clever bits, but we do export it, and so that is a source of income into the country.
I guess from our perspective, we're not the ones creating that over-the-horizon radar system. It's the clocks that fit in there, and at the best, that system's going to require somewhere between 50 and 100 clocks for the next generation. The real opportunity for us are all the other things. So we're working with teams that work in quantum computing. We're working with a lot of astronomy groups around the world. And if every ship in the world with a phased array radar added on a couple of these clocks, that's hundreds, if not thousands, of these clocks that we could sell all around the world. And so for us, that's the opportunity. Australia leads the way in terms of the over-the-horizon radar system. Other countries have looked at it. I believe Russia had a system. The US have dabbled, but Australia's geography really lends itself to having a system like that. But who knows? We shall see. As I say, our focus is more on the clocks than on the radar system, the entire radar system.
Thanks, Piers.
This may sound a little bit linguistically trite, but a bit of poetic license. My question is, how far up the automation, if you like, hierarchies, for want of a better word, are there teams, echelons and/or individuals for whom the whole exponentialisation potentials of all this manifest more like Pitman's common sense arithmetic? And is this the threshold between search and research, so to speak?
Somewhat philosophical. Sorry, I think there are some questions down here. So I'll have a crack at it. You used one of the words you used there was automation. the new Cooperative Research Centre in Trusted Autonomous Systems, the first word is trusted. The most significant challenge we have on the planet with autonomous systems that will make decisions and produce effects on their own, is trust. At the moment, I think Boeing has a capability to provide UAVs that could independently monitor and track some of our long fence lines out in the outback and report back on state and all the rest. They can't operate to do that because we don't trust them. They only can operate within line of sight. So the biggest challenge Boeing has with that capability is not technical, it's all about trust. So Trusted Autonomous Systems as a CRC is really looking at what is it that we need to do, both technically and policy and legally, to get to the place where we actually trust these systems. That's probably really not answering the philosophical question there, but...
I noticed that you talked a lot about modelling every time something significant was implemented. You created a model rather than test in the field. How often do your models come unstuck and predict success when they don't actually work, or vice versa?
Thanks, Bruce.
You cut to the chase, don't you? That's an excellent question. I'll give you that example about the infantry radios. Firstly, we had to, when we were developing the models, we can only have inputs to the models, characteristics that can be measured. We also always validate the models against real-world measurements whenever we can. So certain things were done in the labs and in the field, and measurements were taken, and we had to be able to replicate the results of our modelling to match that. And only then, once the client has confidence in our models, and you're absolutely correct, if the client doesn't have confidence in the models, then we can't sell our capability. So there is a virtuous cycle of modelling, measurement, and then management. If you model it, you have to be able to have enough measurement and to collect the appropriate inputs to it. The outputs of the model also need to be able to be validated. So then you can start exercising the model to derive whatever performance improvements you're after. So very, very good question, and it is a virtuous cycle. You have to validate first.
Yeah, I just wanted to follow up with that. I completely agree with what Bruce was just saying. And in our system, it's very much a matter of validating it continuously. As soon as you start to be able to bring in real components into your system, starting with a complete model without having done any work with validation within that domain before, yes, you're taking a stab in the dark. But as soon as you're able to start to bring in real data, as soon as you're able to start to bring in real components and start to get that information, you're able to clarify, validate, and improve your models so that you're able to get more accuracy as you move forward. So it's not a matter of you build something once and then you let it sit. It's a continuous process of evolution.
My name is Hassan from School of Electrical and Electronic Engineering. I'm a PhD student. Sometimes I face a problem like when we collaborate having these projects, these defense or another, they don't show most of their data or something. They say confidential, and in this case, we need to make assumptions and go on. So have you faced such a problem, and what we should do about it?
Yeah, it's a real issue, and definitely when you're working in the early stages of a project where you don't necessarily have the trust levels or the development to be able to access confidential data, it can be problematic. And that's actually one of the areas that's led us to look at dual use for our work. Because if we're able to validate within non-classified, within non-defence environments, we're able to use that data as a way of being able to be sure about what we're doing as well.
Quite often the work we do is actually classified, and we do work with confidential data. When that's the case, that will be happening on defence premises somewhere, not here at the university. So, but again, as Kat said, that kind of thing doesn't happen without a fair bit of trust developed over time.
Hello. I guess my question's a little bit theoretical. I think it's a good panel to ask it to, being what you all work in. The collection, transmission, I guess also the storage of sunlight and condensed sunlight in order to remove the use of fossil fuels and things in our power generation. I guess it's sort of like is it possible, potentially, in the fields that you all work in, to condense sunlight using mirrors of different shapes and sizes and mathematics and stuff, and then to transmit it somewhere else to change power plants and things so that they're using that sunlight to heat water, to run their engines and everything like that?
I'm going to take a stab that Piers can answer this one.
I was hoping somebody else was going to answer that one. I guess the key is how do you efficiently store that energy? And there's a lot of work going on at the moment with a local company, Heliostat, that are using big mirrors to collect large amounts of sunlight energy. And they're using molten salt solutions rather than water to capture that as heat. And then when you need to get that energy back out, you take that heat energy that's very efficiently captured in those molten salt solutions, and you can turn that back into power. And that's as good a system as I've seen at the moment. I'm not aware of any particularly fancy photonics solutions at the moment for transforming those photons, that light energy, into an incredibly dense form of light energy that can just be moved around on optical fibers. But yeah, I'm not aware of it. Doesn't mean it doesn't exist, but I haven't seen it, and I don't think we're doing it in our labs at the moment. Not yet.
Okay. Hello. I'm interested in... Oh, sorry if I've cut you off over there. I'm interested in how you manage the validation of models for which you don't have access to empirical data to validate against. Is there due process or some standards that you can show conformance to, or is there oversight from an accreditation body or something like that? How do you manage that?
I'm going to have to disappoint you. No, we don't adhere to oversight of standards bodies and what have you for model validation. Look, if there's nothing to validate against, then you have to question what are we doing. Perhaps you have to validate against a model of a subcomponent. Perhaps you can't model the entire system. Perhaps you put together a series of models together where some of them you have validated and you make assumptions about the behavioural characteristics of this last subcomponent that you cannot measure. And that's really as best you can do.
In many ways, we're really getting to the heart of the scientific method, and that is there is a community of people who practice in a particular area, and they publish. They talk to each other about what they do and how they're doing it, and that's really where we get that level of confidence about what we're doing. So even when it's more sensitive stuff that we're doing for defence, we will write detailed reports, and there are scientists at DST Group will review that, give us critique, and it's that community that helps us have that confidence.
Hi. Nearly a generation ago, I worked at a defence-oriented CRC, which DSTO was a member of, and I'm glad to hear that you're now talking about partnerships. One of the issues, I was a business development manager responsible for the intellectual property, and nobody's mentioned intellectual property tonight at all, which is a bit strange given we're in the university. Can you tell me how you handle intellectual property now, especially, say, around the clocks and maybe around software? And what about the students? That was a significant issue a generation ago. Has it been solved?
There are quite a few different models for intellectual property management, and a lot depends upon the details of a partnership or collaboration that you're involved with. But I'll let you say something, Piers.
I mean, ultimately in defence, if the government wants it, they can take it. So, but again, the question's always going to be who's going to actually build a device, because the government often isn't interested in building it. They want to have a company that will do that. So in the question of the clocks, all of the IP in that case is locked up in know-how in the heads of the research team rather than in specific patents. And in that case, the inventors have created a company, CryoClock, and they've licensed that technology from the university. And so they are supplying their clocks, building those clocks outside the university for groups, and talking to the larger organisations around the world, the defence primes, who are interested in sort of taking those building blocks and building them into larger systems. In terms of how we handle IP, again, it's managed on a case-to-case basis. We'll often patent quite a large number of inventions, and in IPAS, we like to split things down into separate fields and license field by field. So in the case of our high temperature sensors, we're working with one partner who've taken a license in the area of kind of metals processing. We've got another one that's in the area of power generation. And so we can carve up a pie multiple times in order to maximise the return to the university.
Thanks. After the statewide blackout last year, there was a small joke going around, what did South Australians use before candles? And the answer was electricity. I was just wondering if that blackout had any impact on any areas of your research and your thinking. A couple of you mentioned the need for power as well as the the control systems.
Yeah, I mentioned the need for power, transportable power for the soldiers in the field. There was a time about a decade ago that it was estimated that I think the average infantry person was carrying something like 20 kilos of batteries on them. Don't quote me on those figures, but it was a ridiculously large number. That's where I was talking about power, was from batteries for the soldiers in the field. We don't do any research on the national power grid.
No. From our perspective, not just the blackout, but also the increases in power have led a lot of companies that have been like the smelter up at Port Pirie, who've been doing the same thing for tens of years, to suddenly want to become much more efficient, understand their processes, and say, how can we make ourselves 20, 30% more efficient? And what we'll discover often is that companies aren't measuring as accurately and as often as they could be. And so it's led to a nice upsurge in work for us as companies realise they can make savings by making measurements.
Yeah, and I think we've seen the similar increase in interest from the tech industry in terms of producing computing hardware, lots of sort of green hardware or low energy hardware, and there's a definite increase of interest as well from defence in looking at that for their potential platforms. So we've seen a push over the recent years, not since the blackout, but before, to investigate those models as potential target platforms for our work as well.
I'm afraid we've run out of time, but I'd just like to ask you to join me in thanking our presenters for their presentations and talks and for the discussion and the Q&A session. Thank you. And also thanks to you in the audience for coming along and listening, and also asking some terrific questions as well. I just wanted to finish by letting you know that we'll be back again on the 8th of August with another exciting Research Tuesday forum on men's health. But actually before that Research Tuesdays event, we're going to have a special inaugural lecture with Professor Chris Helgen, who's an internationally acclaimed mammologist who's just joined us this year. And he'll be talking about his many tales of research discoveries and National Geographic Society explorations and a few hiccups along the way. So you're all very much invited to come along and join us for that inaugural lecture on the 2nd of August. And there'll be more information about that and upcoming Research Tuesday events on the web as well. So thank you all again for coming, and good night and safe journey home. Thank you.